Here are some of the rules regarding parallel circuits. Number 1. The voltage remains the same for each connected load across the applied total voltage. Number 2. The current is divided by each branch or each load across the applied voltage, and the total current is the sum of all the current drops and is the quotient of the voltage divided by the total resistance. Furthermore, with respect to current, Kirchhoff's current law states that the algebraic sum of the current drops will equal 0, and the value of the current entering any node will be equal to the value of the current leaving the node. The third rule of parallel circuits deals with resistance. The total resistance for the circuit is always less than the resistance of the smallest resistor in the circuit and is found by the adding of the conductances of each resistor and then reciprocating the total sum of those combined conductances.
So for Lab 2, we're going to use the same resistors we used in Lab 1. We're using a 33 ohm resistor, a 47 ohm resistor, a 51 ohm resistor, an 82 ohm resistor, and a 100 ohm resistor. I've laid the board out with these jumpers in the same configuration we used in Lab 1. This is to create a series circuit of no resistance. Basically the same as a wire. I've done the same on the other side. The moat separates the two ends of our resistors, so we must connect them all together to make a parallel circuit. I have a jumper for my positive power rail feeding this row. It will carry on to this row through the jumper, through this row to the next jumper, through this row to the next jumper, and so on until the last resistor. I've done the same on the other side, and another jumper that goes from the first resistor, reading from right to left, through the power rail on the negative side. An alternative approach would be to use the fact that the power rail is common. I have my supply going into my positive power rail, and then I've placed these resistors with one end into that power bus. Then I have jumpers forming another power bus on the other side of each of the resistors. From there, I take a jumper that leads to my negative and completing the circuit. Before going any further, I'm going to do some preparatory math. This is a parallel circuit, which means that the current has multiple paths through which to flow. This means that the effective resistance becomes a reciprocal of the sum of the reciprocal resistances. So I'm going to take each of the resistances to find out what the mathematical reciprocal is. So I will take 1 and divide that by 33. This gives me 0.0303. I'm going to repeat all of these so that I can come up with a final total resistance. Now that I've added all of these reciprocal values, I'm going to then divide that into 1, and that should give me my total resistance. We do this before so that we have an expectation of what the measurements should end up looking like. If I did it after the fact, we may make a miscalculation. This way I have my calculations figured out, and when I look at my results, if I don't get the reading that's in the right ballpark, then something's wrong with my circuit. Now that we've done our calculations, we're going to take a look at what the total resistance presented in the parallel circuit is. When you turn your meter on, don't forget that you want to be on ohms, not resistance. Well, let's take a look and see what happens when we do that. I need to go from the start of my circuit to the end of my circuit. Since these are all in parallel, there is not really a start and finish. I'm going to go from here to here and see what I get. Now I'm getting a signal of continuity. We know that with this particular meter, at around about 50 ohms, after 50 ohms it will not release a signal. It will not give us an audible sound. Well, this one is under 50, this one's under 50, but the others, the 100 ohm, is above 50. So is the 82, so is the 51. Our resistance is much, much lower. Let's put it to resistance properly. And let's measure the total resistance from those 2 points again. And it's giving us 10.9 to 11, depending on my contact of the actual surface. Make sure that's set in. Just under 11 ohms. Sure they're all nice and tight. Try it from another point just to make sure. And I'm getting 10.8 ohms. If I check my math, that sounds pretty close. Earlier, I was doing my testing, and I was expecting around 11 ohms. And suddenly, I was getting a number that wasn't even close. 5.7 ohms, 5.6 ohms, that's not even close to 11 ohms. Can you spot the mistake I made? The mistake was not in the circuit I was measuring, but in the circuit overall. I had left a jumper from the demonstration of the alternative method of setting up the parallel circuit. This ends up that I have this in parallel with this. And since their resistances are fairly close, it's like taking the resistance and dividing it by 2. So if I take my 11 and divide it in half, I come up with 5.5 ohms. Let's check the math on that. Okay, so if I take my reciprocals and I add them up and then add them again, I come up with 1 over 0.1846. When I divide that into 1, I come up with 5.417 ohms, which is really close to what I was reading. Now, we're going to do a series of voltage readings to see what the voltage drop is across each resistor. So I'm going to turn my meter on to volts. I have it on volts. I'm going to take my first reading, watching polarity. And I'm getting it jumping and numbers that don't make sense. That's because I have forgotten that right now it is on alternating current. So I'm going to press my select. I see I have my flat line. So let's check our voltages again. This time we're mindful of it. 2.82. My power supply does not put out a perfect 3 volts. 2.82. So you are going to carry on and measure all of the voltages across each of the resistors. For the next part of our lab, we're going to look at and analyze current. We want to know the current that is going to flow through the entire circuit. So we're going to increase our voltage to 4.5 volts. Okay, hopefully my power supply will provide me that. So I'm going to turn on my meter to volts, make sure it's on DC, and I'm going to check my voltage across the entire circuit, watching polarity, of course. And my power supply is putting out 4.56 volts. That's the voltage that we require. Notice that I've opened up the circuit. The workspace is not connected to the power rail. That's because we are taking an amp reading. And again, amps have to be read with the meter as part of our circuit. So I'm going to change my setting. It's now on milliamps. I'm going to make sure that it's not an AC. And now I'm going to insert this into the circuit. So we want to again watch polarity. I've got two hoops that allow me to insert the meter. So I want this to be on the most positive side and my black to be on the most negative side. So I have another loop here. And it says I'm drawing 0.78 amps, otherwise 78 milliamps. We want to now look at the amount of current our circuit is drawing. Before we take a measurement, do the calculations and work out what you expect to see in the current. By now you've done your calculations and you know roughly what to expect. I've altered our circuit somewhat. I've changed the location of our power rail. It is no longer feeding this parallel circuit. In fact, if I were to measure the voltage, it would be 100% of my voltage supply. I've changed my power supply to send a little more than 4 volts, 4.5 volts. So what I'm going to do, I know I've got 4.5 volts going across here. I'm going to set my meter to read milliamps. On my particular model, I'm going to move my red to my 10 amp. That way I can't possibly blow the fuse because I'm only drawing a small amount of current. And I'm going to set it to milliamps. I've got my wavy line, so I'm going to set that to the flat line. I'm going to insert the most positive lead I have into a hoop that I've made. So now the power is coming from my power supply through the rail to my red lead. There is no connection between the power rail and my workspace. So now, in order to complete the circuit, I have to use the meter itself. So I'm going to stick the black into it, and I'm getting 3.8 milliamps. As we learned in our first lab, when resistors are placed in series, they act to divide the voltage, basically by segmenting it with each of the voltage drops. On a parallel circuit, we've already discovered that the voltage is the same. So because we have different resistors, it must mean that it becomes a current divider. I've rearranged my circuit again. This time, I have the power coming through the rail, feeding the parallel branches. But the last resistor in my series, which is the first resistor I want to measure, has been opened up. There is no power flowing through the resistor. I need to complete the circuit. I have put a jumper so that the current, the voltage, will be applied across here to this point. I'm going to put my red lead on that hoop, and it's going to go through the power and it's going to end up with the black. So I'll put my black on my most negative, which is the resistor itself. I'm going to take my red lead and put it into that hoop and connect. And now the meter is becoming the current source. And it's putting out about 1.27 milliohms. You're going to do the same thing, where you're going to interrupt each of these resistors and then restore it and measure the current flowing through each resistor. For the next part of the lab, you're going to conduct an experiment to find out what happens when you stress a resistor beyond its designed wattage rating. In your kit, you should have a half-watt resistor, which will be approximately this size. This would be a quarter, that would be a half watt. So you're going to use a 100 ohm resistor. My power supply will only go to a maximum of 12 volts. Your power supply will go up to a total of 23 or more. What you're going to do is calculate what the stability of the resistor is, what the maximum amount of current that the resistor will take before it fails. And to do that, you're going to need to use the formula P equals voltage squared divided by the resistance. So the wattage is fixed at half. So from each of those you'll use the resistance to calculate the amount of voltage the resistor can withstand before failure.